Very good morning, all of you. Today, we are going to start our unit number 2, that is mechanically energy based non conventional machining processes. Okay, so today I am going to talk about the first mechanically energy based process, that is abrasive jet machining. In short, it is called AJM. Okay, and in this today's lecture, we are going to cover the points regarding this abrasive jet machining. That is, firstly, we'll talk about the introduction, then working principle, then mechanism of material removal, about this EHM, then the setup, that is, we can call experimental setup or system of this agent process. Then in detail we will discuss the elements of agent system. Okay, so in this part one we are going to cover this much points. Okay, in the second part we are going to see the remaining. Okay, so let us start with the introduction and the working principle of AGM process. Okay, and before that also, okay, in of chapter number 1, we have discussed that classification of the non-conventional machining process, and in that we come to know that we have the one separate category, that is a mechanical energy based or mechanical type of advanced machining processes. Okay, and which includes the abrasive jet machining, ultrasonic machining, that is USM, then water jet machining WJM, and abrasive water jet machining AWJM. Okay, so these are the various types of machining processes which comes under this category of mechanical type of abrasive mechanical type of advanced machining processes. Okay, so for that purpose here I have shown the this classification of mechanical energy based advanced machining processes, or you can call non-conventional machining processes. And under category of machining, these are the four processes. Okay, then there are finishing processes also there in this mechanical energy base. So in the second column or second this table, you will get the finishing processes. You can see. So there are finishing process with the help of which we can achieve micro or nano level surface reference value. That surface value, reference value normally it is denoted by RA value. Okay. So in that first you can see one is the abrasive flow finishing, or also it is known as abrasive flow machining also. Okay, AFM. Okay, F or AFM also. Then second is the magnetic abrasive finishing. Okay, then we have the chemo mechanical polishing also, it comes under this finishing process. Then magnetorheological finishing process, and at last it is the magnetic flow finishing. So these are the five processes, finishing processes, which comes under this category of mechanically energy based advanced machining process. Okay, machining category it is different, and finishing category it is different. As per our syllabus we have the machining processes only. Okay, so we will discuss most of these processes in this particular lecture, that is in this particular unit, this machining. Okay, so firstly we'll go with the our first, that is abrasive jet machining. Now before going to this how the abrasive jet machining works, I'm going to explain with the help of the one example. Okay, now for that example you can see this diagram. Okay, so let us see this very interesting picture. Okay, you can see on the slide also, very interesting picture I have shown. So there are two persons. Okay, and they are throwing a ball on the wall. Okay, you can see there are two persons and they are throwing the ball on this wall. Okay, now first one is applying the force F4 on the this ball. Okay, first person, he is applying the force F1 on this ball. Okay, and which is penetrating to a certain depth, that is H1. Okay, and making the diameter D1. Okay, when first person will apply the force F1 to this ball, then ball will hit this wall, and that time by hitting that wall, there will the some penetration will happen, and that depth will be the H1. Okay, certain H1 here I have shown. Okay, H1, and the diameter of that hole D1 only. And the second person, okay, second person is throwing the ball with the force F2. You can see here F2, and it is penetrating to a large depth, okay, H2. Okay, you can see here that force F2 is there, and the depth to which it is penetrating to a greater than H1. So this will depend upon with how much force, and with how much or what velocity the person, first one and the person two are throwing the ball. Okay, in the second case, if you take now example second case, then the velocity or the force being applied on the ball is larger than the first one. Okay, that means the F2 is greater than the F1. Okay, F2 is greater than F1. Okay, and the that velocity or the force being applied on the wall, that is F2 is larger than the F1, and that is why your that penetration depth is no, that H2. Okay, it is also greater than H1. Now in the second case, what are the kinetic energies there, no? So kinetic energy of ball is greater than the case number 1. Okay, and that is why the depth of penetration, that is H2, is larger than the case 1, that is H1. Okay, so yeah, due to this F2 is greater than F1, whatever the H2 is there, that is also greater than H1. So same way we will see that, okay, we will see that when we will have the thousands of average particles, and that are being heated to the workpiece, no? Okay, when we will have the thousands of average particles that are hitting to the workpiece, then they are removing the material from your workpiece, and that time whatever the smaller or more amount of material will be going to remove, no? So that will depend upon the what velocity and the what kinetic energy they hit the workpiece surface. So the basic working principle behind the abrasive machining I have explained with the help of this example. Okay, so whenever your kinetic energy will be high, then the penetration or that depth of penetration will be high, as well as your diameter of that whatever the crater will be there, no, that is also will be high. Okay, so in this diagram I have shown that D2 and the D1 side. Okay, that totally depend on the kinetic energy of the ball when it is hitting the ball, and kinetic energy means what? You can take the force into the mass of the ball. Okay, okay. Now the same principle we have applied in the machining field, and we got this average jet machining. Now here with this diagram I will explain the this average jet machining. Okay, first you just to see this diagram for 1 minute. Now I will explain the working principle of this abrasive jet machining. Okay, how this abrasive jet machining works. Okay, now please look at the diagram which is I have shown on this slide. Okay, now here you can see here is a nozzle. Okay, here at top I have shown the nozzle. Okay, and this nozzle is going to throw the your abrasive particles. Okay, so this nozzle through which this through this nozzle we are going to throw the or we are going to impinge the or hit abrasive particle. Okay, so here is a nozzle through which a mixture of your air and abrasive particle is coming out. Now, in place of air, you can have some other gas also. Okay, because out of the air or other gas we are using this, they will act as a carrier gas for this your abrasive particles. Okay. Now here you can see the distance between the tip of the nozzle and the workpiece surface, no, where it is hitting the workpiece surface. That distance is known as nozzle tip distance. The distance between the this tip of nozzle and the top surface of your workpiece to be machined. No? So that distance it is called nozzle tip distance, which is here are denoted by the NTD. Okay, NTD. Okay, in some book or sometimes it is also called stand off distance. SOD also NTD or stand off distance. Now this air and abrasive particle mixture consists of very fine abrasive particles. Okay, so here I have shown the fine abrasive particles. You can see fine abrasive particles. Okay, you can see here. So this is the workpiece. Okay, here at bottom I have shown. So this is a workpiece from where the material is being removed in the form of small craters. Okay, small craters. That means the your small removed that workpiece part. Okay, so it is called crater. Okay, now as you can see here on the left side, this diagram, the depth up to which that abrasive particle has penetrated or the abrasive particle have penetrated the workpiece, that is called crater depth, and the width to which it is removing the material from the workpiece. Okay, it is that width it is called crater diameter or crater depth. Okay, crater. Okay, you can see. I repeat, the depth up to which abrasive particles have penetrated the workpiece, that is called crater depth. Okay, you can see here crater depth. And the second is that, the width or the that diameter to which it is remove the material from the workpiece, that is called crater diameter, crater depth. You can see here. Okay, now normally depend upon the shape of the nozzle, it can be circular shape. Then you will call it is diameter, that crater diameter. Okay, if your shape of the nozzle will be the circular shape, then it is called diameter. Okay, it can be some other shape. Okay, if the other, then the name will be the accordingly it will change. Okay, so you will have to call it as a width of crater here, width of crater. Okay, now this nozzle tip distance, okay, NTD, okay, keeps changing or it means decreasing as a crater depth keeps on increasing. Okay, as crater depth is going to change, or it is going to decrease or decreases or sorry increases, that time the nozzle tip distance also going to change. Okay, you can see here also that depth, okay, is going to change. Okay, now In that again, if this jet is hitting the top surface of your workpiece, if jet is hitting this top surface of workpiece, then you will have to measure this nozzle tip distance, NTD distance, from the top surface itself. Okay, from top surface itself. But in this particular case, you can see it. Okay, this abrasive particles has penetrated to a certain depth. Okay, so the nozzle tip distance, it is measured from the that depth up to the bottom face of your nozzle. Okay, so you can see this red mark. So that is known as nozzle tip distance, or it is also called stand off distance. Okay, now we have just seen the this how the abrasive jet machining works. Okay, now the small question arises that how this erosion action takes place. That means how material is going to remove from the workpiece. So that scientific reason we should know. Okay. So the question arises. I repeat, how this erosion action takes place. Okay, because due to the erosion only the material is going to uh, removed from your workpiece. Okay. So let us see this abrasive jet, okay, which is consists of the inert gas in place of air into use the inert gas also. Okay, so you can have some inert gas and the fine abrasive particles in this in that nozzle also here. Okay, then the jet at a very high velocity when it hits the workpiece surface. So since abrasive particle have certain mass m and the velocity v, so whatever the kinetic energy is there, no, that means the one half m v square. So the with the help of that or with that velocity or with that kinetic energy, they hit the workpiece surface, and the velocity with which normally this jet or the air average jet moves, no, so it's somewhere near about 300 to 500 meter per second. So it has a huge kinetic energy because velocity is very high. So kinetic energy also will be very high or will be very huge. Okay, so the material removed by the erosion or that chipping action will be carried out or will be takes place, okay, due to the kinetic energy. When your abrasive particle will hit, no, to this top surface of workpiece, so due to the kinetic energy of abrasive particles, the erosion will be taking place on that surface, and due to that erosion, or we can call chipping action, the metal will be removed. Okay, now again question arises that how this erosion action takes place. So the kinetic energy of abrasive particles that will convert into the force, and it will erode the metal, and the kinetic energy of particles is given by 1 half m square that we know. So where the m will be the mass of your individual particle and v will be the velocity with which it is hitting to the your workpiece. Okay, now the again question arises that what kind of operation this abrasive process can perform. So this abrasive machining we can use for cutting, cleaning, polishing, or deburring purposes also. Okay, I repeat, this abrasive machining can do various kinds of operation like cutting up a piece into two pieces, or cleaning or polishing, also deburring, again drilling a hole or cutting a different shape of cavity, then blind cavity we can get from this AGM process, or throw cavity in the workpiece, that also we can do with the using this abrasive machine. So this particular process is more efficient on the hard and brittle material as compared to the your ductile material. Okay, so in case of ductile material, the performance of process is not very good as in case of brittle or hard material. Okay, it can produce fine and complicated details also onto your workpiece. Okay, so here the important point is that how this AGM is going to remove the metal. So the answer will be the kinetic energy of your abrasive jet. And when it will strike to your workpiece, that time due to the high velocity, that is near of 300 to 500 meter per second, the due to that hitting, the erosion action will take place on your top surface of workpiece, and due to that erosion, material will be removed. So here you can see the material removal will be happen using erosion action only. Okay, so kinetic energy of your abrasive particle is going to convert into the your force. Okay, and then erosion will is going to take place. Okay, and here I have covered in short the application also. Okay, for which operation or application we can use this AGM process. So that purpose just I have mentioned here in this slide: cutting, cleaning, polishing, deburring. Okay, also this process is effective on only hard and brittle material. Okay, not that kind. It can produce fine and complicated details also. Okay, understood. Now, with this diagram, now I will explain the mechanism of material removal. Okay, mechanism of material removal in case of this AGM process. So here in this figure, you can see here is the nozzle where you can find air plus fine abrasive particles are coming at a very high velocity. Its range is between 300 to 500 meter per second. Okay, air plus abrasive particles are coming through this nozzle. Okay, now these abrasive particles having or at very high velocity, they come and they hit this workpiece surface. Here you can see the workpiece surface. Okay, now as you can see here, the nozzle diameter normally it is kept in between 0.3 to zero point 0.5 mm only. Nozzle diameter normally it is kept in between 0.3 to zero point 0.5. Okay, whatever this diagram I'm showing now. So this diagram I have taken from the this advanced machining process by Vikajan book. Okay, because normally uh, everybody is taking the reference of that book only. Okay, so whatever the statistic I am explaining here now, so that I have taken from that book only. So nozzle diameter it is ranging from 0.6 to 0.5 mm, and the average jet velocity it is ranging in between 300 to 500 meter per second. Okay, and the gap between this bottom of your nozzle and the top surface of workpiece it is normally around 1 mm. Okay, it is normally 1 mm. Okay, now as you can see here, when abrasive particle hits this workpiece surface, no, then it fractures this workpiece. Okay. And the brittle fractures in the workpiece metal will be there, or when brittle fracture in this workpiece takes place, no, if it is brittle and hard, that time if your workpiece it is brittle and hard, no, that time only brittle fracture will be there. And if your metal is ductile, then the deformation of your workpiece uh, will be takes place. Okay, if your metal will the brittle, then deformation of your workpiece metal is going to take place. And once this fracture has taken place, and then there is a continuous hitting of abrasive particles will be there. That means thousands and thousands of times per second that hitting will be there, and then this fracture material comes out of your workpiece surface, and you will get the cavity which will be created on over your workpiece. So you can see here, okay, how abrasive particles are hitting your workpiece. Okay, if your the workpiece will be brittle and hard, then that type brittle fracture will be there. That is, the erosion will take place, and then material will be removed. And if your workpiece is ductile, then here you will get the deformation. Okay, so through that mechanism, you will get the cavity. That is the shape whatever you want on your workpiece surface. Okay, I repeat, there are thousands of such cavities will be formed on your workpiece surface. So according to the shape of the nozzle exit, okay, and the way in which there these abrasive particles are hitting on the your workpiece, so depending on that you will get the shape of the cavity on your workpiece surface. And here is the worn out particles from the workpiece. that is creating the cavity, you can see, okay, or not particle. Now you can see another thing is that the jet is flowing as it is coming out of the nozzle. No? So that means the diameter of your jet is continuously increasing. So it will depends upon the your nozzle tip distance. So what is the your size of cavity on your workpiece. Okay, so that depends. So you need to keep increasing your nozzle tip distance or that so stand up distance. Okay, so what are the size of cavity is there no? So we'll keep increasing, but the depth it keeps on decreasing as I will show in the next slide also here. Okay, so I repeat that as average particles are repeatedly hit on that your workpiece surface, so you will get the desired shape. Okay, so what are the cavity width will be there, so that cavity width is greater than or equal to the your nozzle your inner diameter. Okay, now what is the actual cavity width? So it will depend upon the stand up distance or the nozzle tip distance. So cavity depth, it totally depends on the workpiece material, feed rate, average particles, and the pressure also. Okay, so that point we need to keep into the our mind. Okay, so this is a mechanism of material removal or the working principle of your average jet machine. Understood? Understood or not? Say yes or no. Okay. In short, I will explain once again. Whatever abrasive particles. Now, abrasive particles means now the types of abrasive particles we are going to in the next slide. Okay. So, air or inert gas we are taking. So, as a carrier gas. Okay. So, due to that, only velocity is going to increase, and that in that air we are going to mix our fine abrasive particles. Okay, which will comes out through this your nozzle and having the very less diameter. Okay, so here whatever we are getting the velocity at the tip when abrasive particles are coming up, so that time that velocity will be the very high. Okay, that velocity is very high means what amount? Okay, 300 to 500 meter per second. And when that abrasive particles with very high velocity, that means very high velocity means that it will have the huge kinetic energy. When it would hit this workpiece, no, when it would strike or impinge on the workpiece, no, that time due to that high kinetic energy, erosion, that means the removal of the small particles from the your workpiece, that will take place. So that is called the erosion. Okay, that means the fracture, brittle fracture will occur if your material is brittle and hard, and if your ductile material is there, that workpiece, that time deformation will take place. So through that uh, action, the material will be removed. Now, the what of the material is removed, it is called crater or debris also it is called. So, debris is called. Now, whenever we are getting the debris, you need to maintain this nozzle tip distance. Okay, so that constant nozzle tip distance need to maintain. Okay, so how does it work? So just taking the summary. So we need to have the jet of average particles. Now average particles, for that purpose we need carrier gas, that is inert gas, and that will strike your workpiece at very high velocity or high speed. So material removal will take place due to the your erosion action only. Okay, understood? This is a working principle. Now I will give you 2 minutes. Okay, so please draw this diagram. Only 2 minutes I will give. Please draw this diagram.
हॅलो सर. सर आवाज येत नाही. ठीक आहे.
अरे अच्छा. हॅलो.
हा
अरे
सर.
म्यूट होतो का
हा
मी? मी
म्यूट होतो
एक्सप्लेन
सर.
करत असतो. ओके ओके सॉरी. वन सेकंड आय एक्सप्लेन.
हा हा.
I forgot to unmute myself. 1 second now. Okay, 1 second. So after this working principle of average jet machining, I was discussing about the experimental setup. Okay, so see here, experimental setup is there. So in this experimental setup or the AGM system, we have different elements. Okay, we have the various elements of this abrasive setup. So first you can see here, we have this compressor. Okay, there is a compressor which compresses the air to the desired pressure in this reservoir. Or you can take air, you can take air where there is a high pressure. Okay, if you want to reduce the pressure of the air inside this your reservoir, no, then you can use this relief valve. Okay, if you want to reduce the pressure of your air, then you can use this relief valve. Then there is a drainage is there, okay, which is connected to this reservoir also. Okay, there is a drainage which is connected to this reservoir, and there is another element which is very important. This is called air filter cum dryer. Okay, air filter cum dryer. Now what are the air is there, no? So air which is going to ahead should be filtered and dried. If it is not filtered and dried, then you will not get the good performance in case of this average jet machining. So here another element is the pressure gauge. Okay, so with the help of this you can find out what is the pressure inside the this reservoir. Okay, again there is a opening wall is there. Here you can see in the red color I have shown, there is a opening wall is there. So again there is the pressure regulator, and here is the main element is the your abrasive feeder. Okay, with the help of this abrasive feeder you can supply the abrasive particles in this chamber. Okay, so inside this there is a mixing chamber itself is there. So where air and the abrasive particles they mix up together in this mixing chamber. Okay, and the mixture of the air and the abrasive particles it will comes out from this. Okay, you can see here. Okay, here you will get the mixture of the your air and abrasive. Okay, again there is a pressure gauge is used. Okay, with the help of which you can measure at what pressure air and abrasive particle jet is coming out. Okay, and here is your nozzle. Okay, so from this nozzle, as you can you have seen earlier also, the jet of your air and abrasive particles is going to come out. Okay, and that air abrasive jet it will hit the your workpiece surface over here. Okay, so what are the distances there? So this distance is known as your stand-off distance or nozzle tip distance. Here is your workpiece. Okay, okay, which is held by the fixture over here. Okay, we have used the fixture to hold your workpiece. Okay, now you can see on the this slide, left side here. Okay, so this is a mixing mixture. Okay, jet of your air and abrasive particles coming in. Okay, air is there. Okay, that means from the your pressure regulator the air will come in this mixing chamber, and in that mixing chamber we have the abrasive feeder. That from that you will get the abrasive. Okay, now the enlarged view of this nozzle and this workpiece you can see here. Okay, this is the. Okay, so here the mixture jet of air and abrasive particles is going to come, and it will both left as well as this right side. Okay, that means here. Okay, by maintaining that nozzle tip distance, we have to go for the that impingement. Okay, so when it will hit this workpiece, That time, the erosion action will take place. Now, how the erosion action is going to take place? Due to the high kinetic energy of this abrasive particles, and erosion action, due to the erosion action, material will be removed from the workpiece material, and then you will get the cavity or out of the machined surface. Okay, so this is a setup. Now, one by one, we are going to discuss this the all the elements. Okay, so this point we will continue in the next lecture. Okay, now I will take the attendance. So I request all of you, please write down your roll number in the chat box. Okay, you can leave this meeting. Thank you.